but it might not be. Let me try to post it right now. I sent it in an email, I know.
I feel like you also have it tucked away somewhere on Blackboard. Or maybe that was last one.
I'll just do a new announcement. Oh, why? All right, I posted an announcement. Another minute or two. Oh, I see you're on chat, actually.
Oh, really?
Yeah. Morning. All right, any questions before we get started?
It's about the atomic weight of magnesium lab. Do you want me to ask you about that later?
What's the question?
When I was trying to find the pressure of hydrogen, I was getting negatives.
So we'll probably have to look at that individually. Yeah. Other questions? So it wasn't a more general one. All right, so let's pick up where we left off on Tuesday with this heating curves. Oops. So now we're kind of going to go through the map. And so let's just look at this heating curve for a second before we start. Oh, one more thing, sorry, I forgot. I wanted to at least mention that your midterm, so it's not next week, but the week after, so week 6 midterm. So we still have lecture next week, so looking at the syllabus, week 5, we'll be doing chapter 16, so starting to get into solutions, probably molarity, I think, is that chapter. And then week 6 will be an exam week, and so like we've done it before, expect a Tuesday review, and then obviously midterm on Thursday. That will take up the whole class plus recitation for time. And then I'll try to write it for like the class time, but that gives people kind of extra time. Yeah.
What is that date?
Let me see. The 9th. Sorry, I don't have a proper calendar in front of me. So any questions about that? And I'll try to make it, a mix of multiple choice and free response. And of course, always show your work. You get plenty of partial credit, but we can talk about that as we get a little closer. And don't forget either about your paper check-in. So I have it again on Blackboard. It's not officially due until the 17th, but again, have it in your brain. Don't forget about it. And just email me, or we can set up a time to meet too if you have any questions about your paper. And I'm super flexible this quarter, so in person or Zoom works for me. Just set up a time. All right, so let's go back to this heating curve. And so we're looking specifically with this one, the heating curve of water. So then if we look at this, so let's see where it starts off at. So this chart, shows it around negative 10 degrees Celsius. And then we have time, which we can also sometimes see these as like energy increasing. So that could be another thing that's on this axis. But basically what's going on as time continues, there's some sort of energy being added to that. And then we'll, again, break down all of these steps in the math. But then we see a plateau here. And does anyone know what happens at this plateau? Yeah.
Phase change.
So a phase change. So anytime you see a plateau, that means that there's some sort of phase change occurring. And again, since we're looking at water, and we know water is going to be a solid here. So of course it's a solid. And now we're doing, if we're going, of course, in the forward direction, this would be melting. In the forward direction. And then, of course, if we're going backwards on this chart, so losing energy, then that would be freezing. And so you notice, right, all the energy goes into the state change. And so once that state change occurs, so now it's done happening, and so now the energy will go back into increasing the temperature of the water, or whatever your substance is at the liquid phase now. And so now all this is going to be liquid phase of water. And so again, just as time increases with this chart, we're adding energy. And so now it's just increasing. And sorry, this got chopped up. That's supposed to be temperature, degrees Celsius on the y-axis. And so we get all the way up to 100. So what happens at 100 degrees Celsius with water? Yeah, what did you say, vapor? Yeah, vapor. So it turns into a vapor or gas. And so we have our next state change. And so in the forward direction, it's being evaporated or turning into a vapor, evaporation. And so what's that called when you go in the reverse direction? Condensation. Excellent. So condensation. And so now we do the state change. Obviously, you can see that requires a lot of energy just with the time. And so now it's all fully converted to the gas stage, and it will continue increasing in temperature then, now as a gas. So now let's break down kind of the math of this. And so there's a couple of terms we need to look at. And so if you were doing this for another substance too, or just doing this on your own, you may have to look up the heat of fusion and some sort of standard table. And so with these things, just pay attention to the units. So you'll see the units that they're given in here, but again, if you look up something on the internet or ask Google, it could be in any other types of units. And so we have our first term is our heat of fusion. And so this is the amount of heat energy required to melt 1 mole of solid. And so right here, this would be your heat of fusion. And so you can put in parentheses, right, melting, freezing. So anytime you're looking at that, you're going to be interested in the heat of fusion. So either melting, how much energy you need to put in, or if it's freezing, how much energy is it going to need to lose. And so melting, again, if we're going in the forward direction, is always endothermic, so it requires energy. And so the delta heat of fusion is positive. And this just means, right, crystallization, aka freezing. Put under here freezing is the opposite, so that makes sense, right? You go in the negative direction, so then you would have to lose that same amount of heat to get it to freeze. And so in general, we're just seeing that the heat of fusions tend to be much less than the heat of vaporization. And again, you kind of got a sense for that in this chart, right? Because the vaporization took just a lot longer time-wise, and we're assuming that whatever energy is being put in is constant, so it required a lot of energy. And so you can at least get a feel for that with these different substances. So water looks like it's around 6, so this is in kilojoules per mole for its fusion versus like 41 or so for the delta heat of vaporization. And you can see that trend holds true for all these other substances, where again, your heat of vaporization is a lot more. And that makes sense, right? It requires a lot more energy to get something from the liquid phase to the gas phase. Are you from Trio?
I am, sorry.
All right, yeah, oh, you're fine. So let's take a little Trio break for a second. And do you mind, I'm just going to put you on camera because I have some people.
Sweet. Okay.
And what's your name?
Haley.
Haley. So this is Haley from Trio. So I know many of you are in Trio, but she's going to tell us why you should join and how awesome it is.
Yes. Hi, everybody. I'm Haley. I'm from the Trio SSS department. I work in there as an office aide / peer tutor. But I just wanted to tell you a little bit about Trio SSS and what it is and how you might qualify and some of the services that we offer. So Trio SSS, first off, is a department at RCC, part of Trio, that is specifically for people that intend to transfer to a 4-year college or university. So that's the first criteria. But you also have to be either a first-generation college student, qualify as financially disadvantaged in some way, which means you qualify for a Pell Grant or some kind of financial assistance, or you have a documented disability. So you have to intend to transfer and then have one of those 3 criteria as well. And if you're unsure if you qualify, they always are really like to get applications, and they'll just go through and see if you qualify. So if you're unsure, they'll go through and do that for you and get back to you. We also offer help with advising. Normally, if you would have an advisor and you're not in the Trio department, it's just an advisor that also has a bunch of other students that are going to RCC. Our cap at Trio for the amount of members we allow in is 155. So you'd get a much more personalized experience with your advisor, and they'd help you out with developing a map, is what they call it, for all your classes and your graduation date. We also offer scholarship workshops that'll help you write your essays if you've never done that before, or just help you go over and review them before you turn them in. They also offer their own scholarships that they give out, specifically from the federal funds that they get. We also offer peer tutoring and like study groups and university tours to the universities that we transfer to. Those are free. You just sign up and they'll take you up there and do a tour. And we also offer snacks. We have just a bunch of food that's free for members that's in the lounge. Yeah, that's pretty much it. I also have peer tutoring applications. You don't necessarily have to be in Trio to apply for this, but this is just if you wanted to tutor someone. It pays $14.75 an hour. Again, you don't have to be a part of Trio. You can just sign up and they'll get you with students.
Will they get you snacks too if you're a tutor?
And snacks, yeah.
I know the snacks is what everyone likes.
Oh, I know, we get so many people that come for the snacks. Okay, well, I have little pamphlets that have more information on them and applications, if anybody would like any. Oh, and the tutoring applications.
Yeah, feel free to hand them out. So raise your hand, and then you can also leave some
Okay.
too.
Yeah.
Yeah, I highly encourage, if you don't qualify for TRIO, because I know not everyone qualifies for TRIO, but if you can at least be like a peer tutor, that looks great on your resume too. And, you know, getting some money never hurts. And at least it's been my understanding that they're always in need of tutors, so. Yeah, and then again, if you don't qualify, feel free to bug me too for resources. Like you have your instructors available. You can always reach out to me for college help and anything. I think there's also a transfer event today, but it's on the Redwood campus. I don't know if they're going to have one on this campus. But yeah, bug your instructors, use all the resources you have.
Anybody else? Good? You guys want one? No? Okay. I will go ahead and just leave some of the
Sweet.
applications here if anybody changes their mind.
Thank you.
Yeah. Thank you for letting me.
Yeah.
Sorry, I showed up a little late.
Oh, you're fine.
Okay, I'll get out of your hair.
All right, thank you. Thanks for the information. All right, so I can't emphasize that enough, right? Bug everybody, bug all the resources you can. Even if you don't qualify for TRIO, you know, you have me. I'm a resource. Bug me, bug your other instructors. Just get what you need, basically. Summer internships, too. Don't forget about those. Summer jobs. Lots of things to think about. Anyways, you can always meet with me individually. More than happy to. So back to where we were. So we're looking at our heat of fusion versus our heat of vaporization. And so you might also have this scenario where something sublimes. So maybe, you know, again, talking about CO2 tends to undergo sublimation, aka dry ice. And so if you were trying to do some word problem and it was talking about CO2 sublimating, but then you can't find, well, what the heck is the delta heat of sublimation? So all that is it's equal to the delta heat of fusion plus the delta heat of vaporization. So you just take these two numbers, add them together, and that gives you your delta H for sublimation. So again, hopefully not too difficult, as you may have to ask the internet for things in your career. And so now looking at heat of vaporization. So the heat of vaporization is just the amount of heat energy required to vaporize 1 mole of liquid. And so again, going in the forward direction, it always requires energy to be added. So our delta heat of vaporization is positive. And then if you're going in the reverse direction, so going from gas to liquid, that would be condensation. And so that's equal to the negative sign of the heat of vaporization. So pretty straightforward. And so now this is just some information. Again, there's all sorts of standard tables. I assume your book has like information like this in the back of the delta heat of vaporization or different substances. And, you know, this is just comparing water. So we know it boils at 100. And then its delta heat of vaporization is 40.7. And always pay attention to the units. So these are given in kilojoules per mole. You could see kilojoules per gram, though, or something, or a different energy unit. So just always pay attention. And then, so this is at the boiling point. So your heat of vaporization at 25 degrees Celsius. It's a little bit different. I would probably just kind of ignore this for the most part. This is the number we're usually interested in. So you can see isopropanol has a little bit lower delta heat of vaporization, and just acetone and ether for comparison. And so that's just part of the puzzle that we need. So right, the fusion and vaporization only help us for these little legs right here. And so the part that we're missing is called the heat capacity. And so the heat capacity is proportional to the mass and the identity of the material. And so each material has a specific heat. So that would, again, be something that you would look up, or on an exam, I would give that information to you. And so now we can quantify the heat if we know the following. If we know the amount, and again, the specific heat, they might give it to us in, notice the units on this one is joules per gram, and then it's over degrees Celsius. So every degree Celsius, it increases, so that's the temperature change matters. But just always watch the units, because it could be given in moles or something if you look it up somewhere else. So just watch your units. And so in this case, again, just our general formula, our heat is equal to, if the specific heat is given to us in this units, then it's equal to the mass times the specific heat times our change in temperature. So just, again, watch your units, watch that everything matches up. All right, so let's go through some practice math and at least see how this would work. So now we're looking at this new scenario. And let's see. We have 1 mole of ice. And so this is just our overall heating curve drawn out. And basically we want to start at negative 25 degrees Celsius and then take it all the way up to 125 degrees Celsius. So we're going to go through this kind of leg by leg, since that's how you're going to have to approach this type of problem. Just break it down each step at a time, and then we'll add up everything at the end to get the total energy. And so the first step, right, first we have to go on our leg 1. So we just have to heat our frozen ice up to 0 degrees Celsius to get it to our state change point. And so that requires our heat capacity. And so you would have to look up the heat capacity for ice. So again, every substance in different phases too has a different specific heat. And so on an exam, I would just give you all these values. And like on an exam, for instance, you could be expected to do this for gold or any substance, basically. And so we're given that, again, we have 1 mole of ice. And then let's look at the units that our specific heat is given in. So our specific heat for ice is 2.09 joules per gram degrees Celsius. So we need to multiply it by our change in temperature. So that's going to be 25 degrees Celsius. So 0 minus 25. And they have all the work written out. So we're just kind of going through it. So that would be 25 times our specific heat. And then, so if your specific heat is given in grams, we started with a mole. So that's why we converted to 18 grams, so 18 grams per mole. And let me pull up my calculator just so we can agree with the number that they're showing us. And so, of course, plug this all in. So 18 times our specific heat times our temperature change. And so we get 940.5 joules. And, of course, you can go ahead and convert it to kilojoules. Just, again, watch your units, label everything, so that when you add them all up at the end, you're not adding like joules plus kilojoules or something. So I'll just highlight this. So there's our step 1. So that brings us to our melting point. And so now we're at the melting point. So that means we need, what value do we need for this? What do we say we needed for our state changes? Oh, I don't know. What's the value called though? Because what's that? So the specific heat though is when you just change the temperature. So that requires some sort of change in temperature. But then what was that called when we did a state change?
Heat of fusion.
Yeah, heat of fusion. So now, right, you look at your curve, you see, oh, okay, we're going to be melting. So that means I need the heat of fusion now. And so we can look it up for water. So this one I think was 4, I have that specific number down here. So the heat of fusion is around 6.02 kilojoules per mole. And so now this is for the molar amount. And notice, right, the temperature doesn't matter because there is no temperature change when you have the state change. So does that make sense? And so again, it could be given in grams. I've seen that happen. But in this case, it's given in kilojoules per mole. So we can just multiply it then by the molar amount of our substance. And obviously, if it was in grams, right, we can convert it to moles, vice versa. And so now we just have 1 mole times 6.02 kilojoules per mole gives us 6.02 kilojoules to complete that phase change. Any questions so far? So now we completed leg 2, right? So we put in our energy to melt it, our heat of fusion. Now we're here. So what value do we need to do leg 3? What do we need to look at? So we're not at the vapor yet, because remember that one was over here.
Go back to the heat absorption equation.
Yeah, or the heat capacity, exactly. So we need heat capacity now. And so anytime you see that change in temperature, so you see the temperature's increasing, so therefore it has to be related back to the heat capacity. And we'd have to look it up. And so again, you have to think, well, what state of matter are we in? And so what state of matter is this? So liquid. So that means we want the liquid heat capacity for water. And so now we're at segment 3 here, heating curve for water. And so you might know this value. This comes up more often just in conversation. But so the specific heat of water is 4.18 joules per gram degrees Celsius. And it's significant since water has a pretty high specific heat. And so, you know, we can talk about the oceans and how that helps keep the temperature regulated on the coast and all those good things. And it's all because of this number right here. And so now we'll plug it in to, again, based off of our units of specific heat. So we have grams, so convert moles to grams, our specific heat times our change in temperature. And so we take it all the way up to 100, right? Because we're interested, we ultimately want to go to 125, but we have to stop at 100 to do our vaporization. So we need to take it from 0 to 100 and figure out how much energy that takes to heat. And so that's what they've done here. So we got 100 for our delta T. And so let's just plug that in so we can agree with their value. And again, this is given in joules. So now this spits out joules, and then you can write it as 7.52 kilojoules. All right, so now we're here at segment 4. So remind me, what do we need again? Heat of vaporization. So now we see it's flat. We're doing another phase change. So we need our delta heat of vaporization for water. And so you would look that up, or again, it'd be provided to you. So 40.7 kilojoules per mole. We have 1 mole of water. So then we can just multiply those two values. So then we get 40.7 kilojoules for that phase change. So again, I'll just write liquid to gas now. And so now this brings us to our last little leg here. So we're at this point of the graph now. So we've gone all the way this far. But the last little bit is it wants us to take the steam from 100 degrees Celsius to 125. And so what value would we need for this little leg? So heat capacity once again. And what phase of matter are we in? What did you say? I'm just deaf. Yeah, so gas, so perfect. And so when you look this up, if it wasn't provided for you, you'd have to look up the heat capacity for water when it's in its vaporous stage. So as you can imagine, it has less heat capacity as steam. And so we have the value here. So the heat capacity, and you can tell, right, it's steam. So this is 2.01 joules per gram degrees Celsius. And so now plug everything in. So again, moles becomes grams. We have our heat capacity, and then our delta T is 25, since we're going 100 to 125. And so we can plug that all in. 18 times 2.01. And so we get this 904.5 joules, or 0.904 kilojoules. And then so the last question would be, well, what was the total energy of this process? So of taking, so what's the total energy to heat ice at negative 25 degrees Celsius to steam at 125 degrees Celsius? And so now all we have to do is add the legs up. So let's start at the top. And so I'm going to do it all in kilojoules just to make my numbers a little bit easier. So 0.941 kilojoules for our first leg, plus 6.02 kilojoules for that melting. And then it took 7.52 kilojoules to heat up the water from 0 degrees to 100. Then it took 40.7 kilojoules to vaporize that 1 mole of water. And then finally, it took 0.904 kilojoules to heat that steam up from 100 to 125. And so now we get the total kilojoules needed for this process, so that was about 56. And I probably can't report to you. I'm trying to see what I did for rounding. So I can report to 2 decimals after, so probably 56.09 based off of my previous rounding. So questions about that process, how to do it?
So it's all the same equation, right?
Yeah, it's just, they kind of repeat the same equation. And you kind of saw like the key point being anytime you have a temperature change, you need some sort of heat capacity. Anytime you have the flat line, then you need some sort of vaporization or fusion. Yeah, well, I don't have a practice problem handy, but probably for our review, we'll do like a harder substance, like, I don't know, probably a metal or something weird that would have unusual answers. Yes?
How would we calculate something if we mix this property with gas laws and we had a container that was sealed with a constant volume, and we're doing taking ice to steam? How would the pressure difference of the liquid to steam change the amount of kilojoules we need?
I'm not sure I fully, so you're saying like if we did the same thing but we just had a closed system? It would take the same amount of energy, maybe more with the closed system, because then you have like a difference in pressure, because this is all at like 1 ATM. So if anything, it might take like more heating.
I was just curious.
Yeah, I'm not sure how to like quantify that at least nicely, but yeah, if you're trying to heat a closed system, that wouldn't be favorable since you have, you know, greater pressure. So then there's like more, because you have to think about what causes vaporization. And so at ATM, right, you're fighting against the pressure. So then if you increase that pressure, then that basically ups your boiling point. So then you have to kind of add more energy. So that's why usually, you know, if you wanted to evaporate something, you always pull a vacuum, and then you don't have to heat it as much. Other questions or comments on this? Yeah, so your question would be, then we're basically raising the pressure, so then you could see how the curve would go higher and higher for its boiling point. And so now we can look at these phase diagrams as well. And so every substance has its own phase diagram. So we're looking at water here. And so our phase diagrams, all it does, it describes the different states that a substance can be in under various temperatures and pressures. And so let's kind of zoom in on this for a second. So on our x-axis, we have some sort of temperature scale. And at least for water, you know, the temperatures that are significant are marked. So obviously freezing and boiling are marked on there. And then we can also see, so we have pressure. And so this is marked as, of course, ATM. So our kind of standard conditions. And then so all this is where water exists as a solid. So you can kind of see, you know, it basically needs to be under 0 degrees Celsius. There's some places where you could maybe decrease the temperature, the pressure, and then that would cause it to sublime, so go from a solid to a gas down at this range. So something very cold, but again, low pressure. So kind of thinking back to your question and our phase diagrams, right, then you start lowering the pressure, and that means that something can boil then at a lower temperature. So that's all this whole block is. So all this is where it's a solid. And then so we also want to note these curves. So if you have the solid to gas, so of course now all this region is where water exists as a gas under these conditions. And so you just want to note, right, where your sublimation curve is. So all this is showing is obviously it's a solid on this side, it's a gas on this side. So crossing this is sublimation. So just note that. And then so up here we have our fusion curve as it goes from a solid to a liquid. And so this means that water exists as a liquid all over here in this region. So obviously, right, more elevated temperatures and a range of pressures, so not too low, but some sort of pressures. So obviously, if you start getting too low of a pressure, then we enter our gas phase here. And again, so anywhere it's touching the solid to liquid, that's our fusion curve. And then our liquid to gas, that's going to give us, right, our vaporization curve, so where it transitions from a liquid to a gas. Yeah?
So if we put a beaker under a vacuum, just a beaker of water under a vacuum, and pull all the pressure out, just at room temperature, it's going to start because there's nothing pushing down on it?
Yeah, exactly. Yep. So if you don't have, right, so you have to think about, yeah, your beaker of water, like literally it's getting beaten down by the atmosphere. So then you start removing the atmosphere, and then those molecules will start escaping out because now they're not fighting against literally the atmosphere beating down. So yeah, it's cool.
Even if there's like no heat or anything?
Yeah, yeah, because it all follows either along, right, this vaporization curve. So, you can see there's all the way down to here to the triple point of like 0, right? So there's basically no heat being added, but you'd still be evaporating out your water. And then you could tell that, right, with this curve as well, as you decrease your pressure, then it boils at a lower temperature. So let's say, you got your vacuum down to 400 torr, so roughly half the atmosphere, which is really reasonable. Then your water, would be pulled off at 80, so you could probably get it way lower. So 200 is about 60. And, we were saying you can get, what was I saying, like 10 to the -3 torr just on a regular vacuum pump. So that's just like your single stage vacuum pump workhorse that every lab would have. So yeah, you can evaporate water, pretty readily, which is like why I joke as a chemist, like I felt like half I was doing was dissolving something in one substance and you evaporate it and then do it again. And that's all you do with these like vacuums and the shrink line systems is you pull vacuum on things and dissolve it. All right, so back to this phase diagram. And so the other thing, or the other key points that we want to look at is the triple point. Let's see, so the triple point, and you can probably tell this just by where it is on the graph, what it means. So notice, right, you have solid, you have liquid, you have gas, all right there meeting at that triple point. So the triple point is the temperature pressure condition in which all three states exist simultaneously. So it looks like if you lowered the pressure a little, then you would reach our triple point where they all exist. And then our other point that we want to look at is a critical point. So it's over at the top over here. And so the critical point is just defined as the farthest point on the vapor pressure curve. And I'm trying to get a nice, that is not, there we go. So I was looking for this picture here. And so kind of the key point with this critical point is that you get this supercritical fluid. And it's kind of hard to describe, so I think the pictures are the best. So the supercritical fluid means that you have a substance at the temperature and pressure above its critical point, and so there's no distinct liquid gas phase. And I mean, to me that doesn't really make sense unless you look at it. And so right, if you're at the subcritical level, you can see there's clearly like some liquid there, and I assume there's some gas there. And then as you keep heating, then that kind of boundary disappears and you have this weird like gas liquid phase thing. And so of course, again, this exists under pretty extreme conditions where you would actually get to observe it. So I've never observed this in my career, but you know, obviously if you were doing research on that, maybe you would get to see that. But you can see, you know, you really have to push that temperature. So this temperature is extremely high. And then you also have, you know, pretty high pressure in there to get it to be at that supercritical phase. And yeah, again, looking back at the picture so you can tell the difference. So there is a distinction between liquid gas and then no distinction. And it's just like this, you know, ball of gas liquid thing. Any questions about this phase diagram? I was trying to pull up another phase diagram, but failing to find one that I liked. And so just so you can kind of see, you can, you know, find a phase diagram for any substance really. So I just plugged in CO2. And again, it would look pretty similar. It's just different numbers depending on the substance, right? So CO2 is going to be centered around kind of its boiling point and its freezing point. So we have, you know, negative 57 degrees Celsius labeled here with our triple point. And for some reason, this one is pressures are in bar. But again, you roughly get the idea. And it's always solid, liquid, gas. Just depends on what substance you're looking at. All right. I'll just plug in another one. So let's see. Let me find one for acetone. It's not always the easiest thing. This one for acetone or just a random one. That's helpful. It doesn't say, oh, iodine. So this one's iodine, just to compare. Again, they just kind of tend to label certain things. So we have 1 ATM. Again, the temperatures we care about. And same thing, so you have your distinct regions of solid, liquid, gas, and everything always has a supercritical point as well. Yeah, questions? Oh yeah, triple point. So anytime, so if you're looking at this graph, they didn't label the triple point very well, but you can see where the solid, the liquid, and the gas all meet there at the triple point. Sorry? The critical point is over here. So that's always, again, like just wherever the farthest point on the graph is, where you have that supercritical fluid, and then the triple point, always where the three phases meet. So on an exam, you might be expected to like label, like if you got a blank diagram, so you'd have to label like solid, liquid, gas, and then triple point, critical point, that sort of thing. And so this is just another graph to emphasize we have our fusion curve, our sublimation curve, and our vaporization curve. Again, going solid to liquid to gas, or solid to gas with sublimation. All right, so let's look at kind of x-rays now. I feel like this is kind of shifting gears. And so this is now how we get pretty pictures from our crystals and what we do. And so how this works is, so let's say you're doing your research and all that good things, and you have your data, but what you really want is a nice crystal picture of what's going on. So this basically gives you like a picture of your molecule. And so how they do this is, sorry, I'm trying to also look up an X-ray machine. I can't talk and type. And so basically, you take your little crystal, and it has to be grown very nicely for this to work. So this is where science becomes an art. But if you can pick out what's basically a single crystal, now you can hit it with some X-rays. And let's see if we can get some pictures. I'm not crazy about any of these pictures. Here's a decent one. So what I'm trying to emphasize is like your crystal gets mounted on this tiny little point. So you have the smallest crystal, and then the X-ray crystallographer, if you're lucky enough to have one, or otherwise you have to do it yourself. But then you mount your tiny crystal on there, and then it gets bombarded with these X-rays. And so just so you can see with these pictures, it creates this diffraction pattern. And so you see when the X-rays strike your parallel plane of atoms or molecules in a crystal, so that's why it also has to be a nice, well-defined crystal. Then you have constructive interference if the difference in path length between the beams reflected from adjacent planes is an integral number of wavelengths. And so again, all that means is you get this pretty diffraction pattern. And so we have Bragg's law here that helps. So you have your constructive interference occurs when your 2A is equal to your wavelength. And so what this gives us is a pretty picture, basically. And so now this is kind of explaining how you get a nice crystal lattice formation. And so, again, this is, you can see this when you make rock candy or if you recrystallize your table salt if you get bored. And so if you allow something to cool slowly, then the particles tend to arrange themselves to give maximum attractive forces and then, of course, be a crystalline solid. And so what you get from this diffraction pattern is you basically get not only the pretty picture, but it tells you kind of how your units are arranged. So it tells you like your unit cell and then kind of what crystal it is. So the arrangement is called our crystal lattice. And so this is good vocab. So the smallest unit that shows a pattern of arrangement for all particles is called a unit cell. And And so unit cells are just 3D structures, so they usually contain 2 to 3 layers of particles. And so they may contain, right, more than one molecule. And they're repeated over and over again to give your crystal structure. And so starting anywhere within the crystal results in the same unit cell. And so this is what you want to kind of take away from this. And these are just kind of the main 3. So you can have crystals that crystallize in like other patterns as well. And so the first one is this basic simple cubic structure. And so you have one whole atom per unit cell. And so notice you kind of have like 1/8 of each little atom in there. And so it has a coordination number of 6. And then the edge length, so this would be related to your atom, would be 2R. And then so packing efficiency just gives you a rough idea of, again, like how much volume is occupied or not. And so this one is kind of less packed. And so this is only 52%. And so let's look at this picture for cubic unit cells. So again, you have one whole atom in there, but you only have, right, 1/8 of each little corner particle. Yeah.
What does the coordination number correspond to? It's in the little chart.
Yeah, so coordination number, it's basically like how many it can be bonded to. So then we have 1, 2, 3, 4, 5, 6. So that's where that 6 coordination number comes into right here. Yeah. And so really the key is you have, again, one atom per unit cell, with all being 1/8 of those atoms in that unit cell. So again, you have 8 atoms displayed in here, but then 1/8 of those atoms as at each of those corners. Now let's look at bodied centered. Oops. Oh, did I not put a body centered one? So looking at body centered, it's pretty similar to cubic, except now we have something in the center there. So you still have kind of 1/8 of these in there, but then now you have an additional atom on the center. And so let's look at other bodied centered cubics. I was hoping for it to show examples. And so looking, and again, you would just have to take a crystal structure to know this. So lithium, sodium, potassium, vanadium, all of these have this body-centered cubic crystal structure. And so this is just telling you what atoms, what they tend to crystallize in. And so you can see there's a lot of different shapes too that we're not covering. So we just looked at simple cubic. Let's see, is there anybody that's simple cubic on here? Polonium? Oh yeah, you're right. Good memory.
I think it said it was the only one though.
Just trying to get a better picture. And so this is cool. So this is the Crystal Structure Database, CCDC. And so literally every compound that is made gets reported to this. So then you can search it and look for it. So that's like the other beautiful thing about this research is you get this pretty picture, you upload it to the database, and now it's kind of like your individual molecule now. And so people can look at it, they can see, oh, look, somebody else made this compound that I may be interested on. And so there's polonium. Again, you can see how there's 8 of them, 1/8 in each one. So let's look up, so lithium, crystal structure. And so now we can compare, so again, lithium looks pretty similar to that simple cubic, except now there's an atom of lithium in the center as well as having one on each cube there. And so now, and here's the other, again, key point. So our atoms per unit cell, so our body's center now has 2 atoms then per unit cell. I like putting our examples. So polonium, and then we could put, right, lithium for this one. And then edge length, again, in terms of radius. So now we use 4r over the square root of 3. And then you can just at least appreciate that it has a greater packing since now we have something in the center. And then so now for our face-centered cubic, now we have 4 atoms in our unit cell. So that's something you might want to know. So 4 atoms. And so let's go back. Let's see, we have. And so here's another picture of our face-centered cubic now. So now 14 particles, so we have 1/8 on each side still, and then now we have 1, 2, 3, 4, 5, 6 halves. So that gives us 4 particles, so you can see the math drawn here. 8 corners times 1/8 plus 6 half faces. And so that gives us 4 total particles in there. Let's go back and look at some other pictures. Oops. There we go. Lost mine. So then we want to find a face-centered cubic example. So it looks like calcium. And so now let's go calcium. Crystal structure. See if this gives us a pretty picture. It's not the best picture. Question?
More of a thing to share. Did you hear about, there was some research done on Roman hot concrete, which included, little chunks of lime in the, concrete itself, so that, when the concrete cracked and there was a rainstorm, the concrete would self-heal because the calcium and the lime would dissolve into the rainwater and calcify the cracks.
Oh, that's cool. I had not heard of it.
I just thought it was cool, and since we were talking about calcium.
I don't like any of these pictures. Blah, blah, blah. I was trying to find a better picture of face-centered cubic, but.
So did you create crystals when you were doing your PhD?
I did. I was gonna try to look at them, but I don't know that I can readily. I can pull up my thesis and look at pretty pictures, but I'll try to pull up at least my thesis to look at pretty pictures in a second. All right, so we'll move on for now. But again, just kind of key points of this is how many atoms in each unit cell. So if you were given problems, it may depend on that. And then this edge length would also probably be key in some sort of problem. But we'll do examples before your midterm. All right, so let's look at classifying our crystal solids here. And so we can have kind of our crystalline solids. And this could either be molecular or ionic solids. So of course, molecular solids tend to have lower melting points versus like table salts or something that's an ionic solid. So that's going to have high melting points. And then we can also classify things by just atomic solids. So composite units are atoms. And so this could be non-bonding, like xenon. So solid xenon, of course, that would have to be right at an extremely low temperature, so low melting point. What do we say? I want to say it was like 160 Kelvin or somewhere around that order. So only held together by those London dispersion forces. And then you have metallic bonding, which we'll look at in a second. So metallic bonding is a little bit interesting. They kind of make what's called like a sea of electrons, and they tend to delocalize and then all bond together by these kind of metallic bondings. And they tend to have a much higher melting points. So you probably know that with gold or other metals. And then your last type would be these network covalent solids that are held together by covalent bonds. And so these would have high melting points. So for example, quartz would be a good example, or diamond or something. So again, covalently held together and high melting points. And so these are just more examples. So I think we all know what ionic crystals are. So those are just ionic compounds. So sodium chloride, potassium chloride. Your molecular crystals, so that could be iodine, looks like that's sugar, carbon dioxide. And then network crystals, right, are extended network, so that could be carbon, aka diamond, or silicon dioxide, aka glass. I'm not sure what silicon carbon is. I'd have to look that up. And then something that's amorphous is going to have a lack of a sharp melting point, and that can be a mixture of things, you know, glass, plastics. And then again, those metallic crystals are anything that's metal. And the key point is that they're good conductors of electricity. And again, we'll talk about those sea of electrons. Skip over that.
It looks like silicon carbide is carbonium, which is a semiconductor.
Ah. That makes sense, silicon carbide. And so we have these other mixtures that we can classify. And so you can have a colloidal mixtures. And the particles in a colloid, what makes it a colloid is that they're large enough to scatter light. And so you get what's called the Tyndall effect. And so that makes colloidal mixtures appear cloudy or opaque. And so this is just an example of a dispersion of gold in water. And these tend to be like nanoparticle size, or can scatter light. So you can, if you boil your solution appropriately to make nanoparticles, then you'll get this kind of solution. And so there's other examples of colloidal dispersions. So for example, you're probably familiar with like fog or mist or, smoke. So if you like blow out smoke or you see like fog, obviously, the danger with fog is that it scatters light. So that's the whole Tyndall effect, is that you're not quite sure where the light's coming from since it gets scattered and bounced off by all the particles. And so same thing with like dust, right? So I'm sure you all have seen dust in the light, right? You have like a stream of light coming in, you smack your couch or something, a bunch of dust flies up, and then you see, right, all those particles. So that's the same thing of the Tyndall effect. And so other examples would be like whipped cream, shaving cream, your paints would be another example, mayonnaise, detergents, and then oil-based paints as well, blood, clay, all those are examples. You can also have like solid gas mixtures, so that would be your pumice stone, so you see it has all the holes left over. Cheese is another example, and gelatin. And then your gemstones would also be solid examples. And now I don't remember why I have a soap here, but soap is pretty cool. Since how soap works is it has a non-polar part to dissolve all those greasy fats, and then a polar group to get it solubilized in water. And so then you have, right, this grease gets surrounded by your soap, and that forms your micelle, and then it all washes away nicely.
Are bars of soap clean?
Or what, are bars of soap clean?
Yeah, I feel like the first time you use them, they are, but after that, like, what does the grease just like stay on there, or where does it go?
I mean, it should just like wash down, wash away. So yeah, you gotta wash your soap, I guess, but I guess it's like a more philosophical question. Maybe some biology experiments, like you need to swab the soap, and see if you can grow a culture.
I feel like it's in the same context as, is a hot dog a sandwich?
It's hot.
When you wash the soap, more soap.
See, that's. Anyways, I'll leave those questions for
Sanitize the
biology.
soap.
Yeah. So let's look at this last little bit and explain what the heck is metallic bonding. And so what is band theory? So band theory kind of puts together our metallic and covalent solids and our MO theory, just kind of all together. And so you have metals and covalent network type solids results when atomic orbitals of these elements form molecular orbitals. And so basically they just become shared throughout and are delocalized. So that's where that sea of electrons is coming in. And so we have, right, when two atomic orbitals combine, we said that they produce both a bonding and antibonding orbital. We just saw that. So just thinking back to basic H. So bonding and antibonding. And so then if you have n atomic orbitals combining, they produce n/2 bonding and n/2 antibonding. So that's all that's saying, right? We put two orbitals in, and then half of those are bonding, half of those are formally antibonding. Except when you have now this like sea of metal electrons, you end up with a bunch of atomic orbitals that have basically the same energy. So we started with, again, this is hydrogen, except now if we're looking at, let's say, sodium, and so now we have a bunch of sodium atoms coming together, and so a bunch of 3s orbitals that are basically the same. So now you get, right, very little separation, and so now they are become delocalized, so now our electrons, right, can go all across too. And what you get here is now we're starting to combine. So this would be lithium, so single lithium, looking at the valence electron, has one valence electron. Now we combine two, so now we have, right, our bonding, our anti-bonding, fill up our electrons. And then we just kind of continue until we make, right, this infinite lithium N, because now we're thinking of a huge chunk of metal, lithium N. And so what you get is called basically your valence bands versus your empty orbitals, your conduction bands. And so now, right, the energy levels of your molecular orbitals are very closely spaced, that they just essentially become your band, or half of the orbitals are bonding and contain electrons, and the other half are anti-bonding. And so now we can explain the difference between a conductor, a semiconductor, and an insulator. So this just depends on your energy gap between your bonding and anti-bonding. And so we say the band of a bonding molecular orbital is called our valence band. And again, this is just for metals, we're talking about that. And so that means that our band of anti-bonding molecular orbitals is called our conduction band. And so as the temperature rises, some electrons may acquire enough energy to jump to the conduction band. And so the difference in energy between your valence band and your conduction band is called your band gap. And so, of course, the larger the band gap, then the fewer electrons there are to make the jump. And so now this explains the difference between a conductor, semiconductor, and an insulator. So something that's a conductor has a really small or no energy gap. And so that's why metals are really good at conducting, and so electrons can easily make this jump. And then if you have a semiconductor, it has a small energy gap that maybe can be overcome under certain conditions. So a lot of these semiconductors work like at really low temperatures. So you change that, and then they are able to make this jump from the valence band to the conduction band, making it a semiconductor. And then if you have a large band gap, so where they can't make that jump, then that's going to be called like an insulator material. Any questions about this basic thing? And then the last little bit is how crystals form here. And so we have an illustration of the different ways a crystal can kind of arrange itself. So you have your nice solid crystal, and then this would be a liquid arrangement of crystals. So now you can see they're not perfectly aligned. There's disorder in there. And then in a smetic phase, the molecules are aligned in layers. So this might come up as vocabulary. And so notice, right, there's a distinct layer there between these two crystal structures versus a nematic phase where they're still aligned, so they're still going up and down, but then there's no like arrangement of layers. So now they're kind of overlapping there.
So are the smetic and the nematic both solids?
Yes. So they both be solids, but this one has molecules arranged not as neatly.
Would pneumatic crystals be that of those crystals that kind of like when they get broken off, there's like little long fibers? Would that be?
Yeah, that would probably like describe them, because I would say the smetic would make more like blocky crystals, and yeah, so the pneumatic would make like the little shards. And these would probably not make good like crystals for X-ray diffraction. All right, I think we covered everything. I did at least find my thesis, if anyone wanted to look at pretty pictures or not pretty pictures. I mean, I think they're pretty, but what is this? So this, I think, was one of my coolest compounds. And that it got the closest to saving the world. So the whole goal was to save the world by converting CO2 to methanol. That doesn't happen very nicely. So here I have like two palladium-looking things, and I have silicon bound here. And so basically, it took two equivalents of CO2 and made formate, but then just kind of attached there. So you have carbon with 3 oxygens. And ideally, in a catalytic cycle, you'd be able to add some sort of proton source to it, and then it would make methanol or something cool, but I just kind of looked at you. And yeah, this is a pretty picture, though, that X-ray crystallography gives you. And you can look at all the other fun data. So this is what data looks like. Trying to find other pretty pictures. Oh, those aren't crystal structures. So more pretty pictures. So I like to say I made a bunch of useless air-sensitive compounds that didn't do anything, though. So this is like a iron dimer, and it has like a little CP ring attached to it. Here's more stuff. So this is CP star. Because remember when I was going on about like metals attaching to benzene and stuff like that with MO theory? Roughly, vaguely. So that's essentially what I was doing, some sort of metal, and they like to be bonded to either CP, which is that, or CP star, which is that compound with methyl groups. So more pretty pictures, so manganese compounds, so not a dimer, and they just have a bunch of COs on them. And so talking about CO reactivity, notice how it binds at the carbon, so that's kind of cool. And you guys can kind of explain why now from MO theory. All right, I'll stop boring you with pretty pictures. All right, let's go ahead. I think we're out of and overtime. So let's take our 10-minute break before doing our quiz. And happy to look at more pretty pictures.